Okay, so let me go to the calendar here. Oh, you guys can pick up a key for packet 5. There is the FRQs and the keys packet. So sorry if it ran out that you weren't able to pick up one just now. So tomorrow we're going to have the multiple choice portion of our second part of our multiple choice test, which is over integral topics. So we did problems 1 through 8, and then 9 through 16, or it'll be another set of 8 problems, 25 points. It's meant to be, again, meant to be a 30-minute test, but giving you guys the full period. So if you guys can review pages 9 through 12 and then 19 through 22. I'm creating another practice worksheet just for just some miscellaneous integral problems. So I should have that ready maybe later today. So if I can get it ready before the end of the day, I will send out a remind that you can come pick it up. But I'll also send you guys a PDF link if you want to just work on it tonight. But tomorrow morning, I can work through those pages, 9 through 12, 19 through 22, or highlight some problems there. And then I also have some, I also have an additional worksheet that we can do tomorrow if you want some additional problems to work on tonight or tomorrow morning. Okay. Okay, so today I would like for us to start on our FRQ packet. So these are packet 5, which is going to be a completion grade, but this will go towards individual standalone quiz grade. So it should be an automatic 100, assuming that you are showing me all the homework on time. So I'm going to be pushing out some of these dates a little bit because we're starting packet 5 today instead of last Friday. So on Wednesday, I'll check pages A through I, but each day I will send out a remind with the pages that's due the following day. So because we're going to be a little bit, it's going to be different from your calendar. So we're going to be a little behind, like maybe a day behind in the calendar, but we should be able to get all of our packet 5 done by next Tuesday. And then I'll try to give you packet 6 later this week if you want to start working on that. Packet 6 is a set of multiple choice tests and miscellaneous problems. And packet 6, I won't be checking that on a daily basis. You just are going to just try to finish that before the end of the school year. So you should show that to me by the end of the school year to get 100 on that quiz grade as well. Any questions with today, tomorrow, or the rest of the week? All right, so let me ask you this. Are there any questions from 19 through 22 that you want me to go over with you? Okay. All right, so let's start looking at packet 5. Again, there's packet 5, and then there's the key packets that is next to it. Okay, so this is the actual FRQ from last year, 2023. So why don't we read through it and then see if we can decide how to build our answer here. Okay, a customer at the gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function F. So look at F here. This is already in terms of a rate. This is gallons per second. So 60 seconds in, the rate that gas is entering into the gas tank is 0.1 gallons per second, then 0.15, then 0.1, then 0.05, and then at 150 seconds, we stopped adding gas to the gas tank. Okay, using correct units, interpret the meaning of the definite integral from 60 to 135 of f of t in the context of this problem. So we know f of t is starting as gallons per second, but if we take the integral, if we're accumulating this rate over a period of time, then what unit is this going to be referring to? It's still going to remain gallons per second? Just gallons, right? Because the idea is that with integral, we're multiplying units. And you're doing gallons per second times seconds. You're accumulating that gallons per second over a time interval. And then over that period, what you're going to accomplish is you're going to be able to know in terms of gallons. What do you think this means then in terms of gallons? From 60 to 135. What does this mean for us for this problem? Yeah, the amount of gas in gallons pumped into the gas tank between 60 seconds and 150 seconds. Okay. Okay, and then we want to use right-Riemann sum. Okay, with the three subintervals provided. So we want to go from 60 to 90. That's one subinterval. 90 to 120, and then from 120 to 135. We want to do the width and height. Okay, so for the first rectangle, what's the width of my first rectangle? 30. Okay, and what's the height of my first rectangle? Good, because I want to use right-Riemann sum, right? Yep. So width times height, and then we just go down the line. Width times height, width times height. Everything's in terms of gallons. Okay, try that. This is a number one. So this is number one on FRQ. So this is a calculator question. Okay, part B says, must there be a time, or must there be a value C, time value between 60 and 120, where f prime of C is equal to 0? So we don't see a f prime where we can look at a set of values for f prime and see f prime is 0. But what's f prime? F prime is what? Derivative, right? Or the slope. So can we guarantee a slope of 0 somewhere between 0 and 150? So slope 0 would mean that you have 2 points that are the same y value to force a slope 0 in between, right? So do you see 2 of the same y values? Yeah, so 0.1, 0.1, right? So if I find the slope between these two endpoints, I get 0.1 minus 0.1. That's 0 over 60. So I can guarantee, so if you imagine that your graph looked like this, so at 60, it's at 0.1. And then at 120, it's hitting 0.1 again. So somewhere between, the graph has to, or it could go up or go down. It has to experience a slope 0, right? So that's, you can say mean value theorem or Rolle's theorem. I said Rolle's theorem, but yeah, we can say that, just have to be able to state that we're applying Rolle's theorem or mean value theorem, that our function, our f of t is differentiable and continuous. So we know that's a smooth curve, and I can identify 2 points that have the same y value. So the slope between those 2 points is 0. So if my average slope is 0, then there must be a precise 0 slope somewhere along that curve. Okay, part C. The rate of flow of gasoline in gallons per second can be multiplied by g of t, this messy function here. Find the average rate of flow of gasoline over the time interval from 0 to 150. So find the average rate of flow of gasoline. What does that remind you of? What formula can we use there? Average value theorem, right? So this is just a purely, identifying that formula, put into the calculator, and then what's the units of measure going to be here? Is it gallons per second, or is it gallons, or is it gallons per second per second? Yeah, just gallons per second. Yeah, average rate of flow of gasoline. Okay. So all this can go in your calculator. Here's our formula: 1 over b minus a. What are my a and b values? Yeah, 0 and 150, right? So it's really just this straightforward as just putting into your calculator, right? So you do math 9, or do 1 over 150, math 9 from 0 to 150, and then plug in your g of t function. Make sure you use x instead of t, and then, yeah, so all that can just be entered in your calculator. Part D, using the model G defined in part C, find the value of G prime of 140. So what do you think G prime is going to be? What's the unit of G prime going to be? Yeah, gallons per second squared. So this is going to tell us whether the rate that gas is being pumped is increasing or decreasing, right? So if we get a positive number, then we know that the rate of the pump of gas added per second will be increasing. But if we get a negative number, we know that it's going to be decreasing. So this is again a nice calculator question here. There's no need to work it out by hand. We can just do math 8 and then use the function that we put into our calculator, math 8 140, and that'll give us a decimal value. If we get a negative number, we know that the rate is decreasing. Yeah. Oh, you're going to type in this g of t function here. Yeah. So you do x over 150, x over 500 cosine of x over 120 squared. Oh, yeah. Okay, so I would consider this problem like an easier FRQ because everything is, I mean, part B, if we recognize Rolle's theorem, mean value theorem, we should be able to recognize that. And then C, if we recognize the average value theorem, it's just calculator. And then D, we know the second derivative is just the rate of change of first derivative. So this is it'd be nice if we get a problem that is this straightforward on the AP on our AP exam. But this was number 1 from last year. Okay, let's do number 2. Number 2 is a particle motion calculator question.
You're like one shorter one longer one.
I'm sorry?
Right, presuming that.
There'll be 6 FRQs. Yeah. Every FRQ, the number 1 and 2 will be calculator, and then 3 through 6 will be non-calculator.
Are you all the same length?
They all have at least 3 parts. But I think they all range between 3, ABC or ABCD. Yeah, but having said that, there are FRQs that will go a little faster than others. So hopefully there are some FRQs that you can solve under 15 minutes. And then that way you can reserve the time that you saved on one FRQ onto another FRQ that may take a little longer. But they give you an average of 15 minutes per FRQ.
And the calculator, non-calculator are separate.
Yeah, so 1 and 2 are calculator. After 30 minutes, you have to put your calculator away. And then you can work on the rest of the problems, but you can still go back to 1 and 2. You just can't use the calculator after 30 minutes. Okay. All right, number 2. Steven swims back and forth along a straight path in a 50-meter long pool for 90 seconds. So let's imagine that happening. So the only thing Steven can do is just going to go back and forth along a 50-meter length pool, right? Either he's going to quote unquote forwards, or he's going backwards, or he's at rest. Right? So there's only 3 things that we can imagine for our path of the swimmer. Okay, so Steven's velocity is modeled by v of t. So it's a messy function, but it's okay. Our calculator can handle it. Where t is measured in seconds and v of t is measured in meters per second. So that means if I plug in a t value, either 0 seconds or 5 seconds, I can figure out exactly how fast Steven is moving, right? If I get a positive value, I know he's moving to the right. If I get a negative value, I know he's moving to the left. If I get a 0, I know he's at that moment, he's at rest, he's not moving. Okay, find all the times when Steven changes direction. So changes direction, that means when velocity is going to have to first be what? So there's 2 things that's happened. If Steven's going to change direction, he first has to reach a velocity of 0, and then there has to be a change in direction, right? Okay, so why don't we create our velocity sign line then? Or let's graph the velocity function and then look to see where Steven changes signs, right? So if he crosses the x-axis, then we know he's moving right, stopping, and then moving left. So there's a change in direction there. So we literally just have to just graph it and look for any sign change. Okay, so in our calculator, we can go ahead and do y equals. Okay, I'm gonna type this in here. So 2.38 exponential function e to the negative 0.02 times sine of alpha trace, alpha y equals will give me that nice math print, pi over 56 x plus parentheses. What should I set for my window here? What do you think would be a good x min x max for this problem? 0 to 90, right? We see that, this is for 90 seconds here. That's our t value. So I'm gonna go from 0 to 90. And then for y min, y max, I'm just say from negative 10 to 10. I may have to adjust that later. But it's important that we can establish that x min, x max. So we can kind of just focus on where the graph is going to cross the x-axis. Okay, so this is pretty good, right? So how many times is Stephen going to change direction? Just once, right? He's going to move to the right, and then he's going to stop, and he's going to move left. So just to figure out where that x-intercept is. So if you do second trace, we're looking for 0. We're looking for an x-intercept. Pick a point to the left. Hit enter. Pick a point to the right. Hit enter. Hit enter a third time. And then you'll get x equals 56. So this 2.33 times e to the negative 13, that's basically a 0. That's just indicating, okay, we can just assume that's 0. And so we can say at 56 seconds, that's when Stephen's going to stop, probably hit the wall, stop, and turn around. Part B, find Stephen's acceleration at t equals 60 seconds. So acceleration is the what of velocity? Derivative, right? Do we have to do this by hand here? No, just make the calculator do it right. We'll do math 8, and then plug in that function and type in 60. Show the setup for your calculation. Indicate the units of measure. Is Stephen speeding up or slowing down? So how do we determine speeding up or slowing down? Do we just look at acceleration, or is there something else? Yeah, we got to compare what? Compare signs. Yeah, speeding up would be both velocity and acceleration are positive. Slowing down would be positive one function and negative the other. So I already have my velocity function plugged into y1. So if I do math 8, d over dx, alpha trace y1, I'm just going to type in 60, so I can find out the acceleration at 60. So negative 0.179, that's a negative acceleration. Let's see the velocity at 60 seconds. So if I do alpha trace y1 of 60, my velocity is negative 0.519. Oops, sorry. Sorry, I messed up here. I didn't type in my function correctly. I didn't type in 0.02x, so let me try again. All right, negative 0.03 and negative 0.159. Okay, so the signs are the same. What does that tell us? Stephen is what? Speeding up, right? Speeding up. Yeah, so acceleration is meters per second squared. Velocity is meters per second. Same signs. Part C, find the distance between Stephen's position at 20 and position at 80. This is simply displacement. It's just integral from 20 to 80 of velocity. And then part D is distance. So we just have to do the exact same formula and put absolute value around it. So this is a nice, easy FRQ problem, right? Very straightforward, nothing, if we know our rules of displacement, total distance, and comparing signs. We're gonna look at different years, and there's some years that the problems are more challenging, and years that that they're not. So it really just depends. But on their end, they're always monitoring. Once they grade the exams, they're always monitoring how students are doing, and they're always slightly curving potentially some problems. If everyone is scoring poorly on an FRQ, they're going to curve it to the point where the average scores will still remain the same. So if everyone is struggling on the problem, then they're typically adapting the scoring that way. So that's why I think when you receive your AP score, you'll get either a 1 through 5, but you won't get your raw score. I think they're holding that raw score. They want that flexibility to be able to change and adapt the raw score to meet 1 through 5. So every year, the requirement to get a 3, 4, 5 is slightly different depending on the test and students.
How much are the multiple choice questions weighted compared to that?
Half and half. So multiple choice is half your AP exam grade, and then your FRQ is half your other. Yeah, so it's exactly 3%.
Is there a break between multiple choice and
Yeah, like a 15-minute break or so. Okay, let's look at part C. Okay, so we're moving into the non-calculator section here. A bottle of milk is taken out of the refrigerator and placed in a pan of hot water to be warmed. The increasing function M models the temperature of the milk at time t, where M of P is measured in degrees Celsius, and T is measured in minutes since the bottle was placed in the pan. M satisfies the differential equation, dm over dt equals 1/4, 40 minus M. At time t equals 0, temperature of the milk is 5 degrees Celsius. It can be shown that M of T is less than 40 for all values of T. So temperature of milk is never going to be over 40 degrees Celsius. A slope field for a differential equation is shown. Sketch the solution curve through the 0.05. So if you're ever asked to sketch a slope field, you're just literally going to follow where the graph is headed. So we know that we have to go through this point. We're just going to follow the path of the graph. We see that dotted line is indicating that there is a horizontal asymptote here. So really just as easy as just following the path of the graph where it takes you. Part A, yeah, so that's part A, right? Okay, so good. So part B, use the tangent line to approximate M of 2, the temperature of the milk at time t equals 2 minutes. Okay, so tangent line. What information do we need for tangent line? Point and slope, right? So usually point is xy, but what variables are we using for our problem? Instead of xy, it's going to be what? T and M, yeah. So we want to adapt accordingly, gather our ordered pair. Your tangent line equation is also need to be adjusted. And what point are we going to use? 0.05. Okay, how can I find the slope? Into my dmdt, right? So do I need a t variable to solve my slope? Just what? Just the m, right? So just plug in 5 in for m. So I get a slope of 35 over 4. I have my ordered pair, I have my slope, tangent line. I typically have, this is my tangent line equation, but what adjustment do we need to make with our tangent line equation? Instead of y minus y1, we're going to say what? M minus M1. Instead of x minus x1, I want to use what? T minus T1, right? So just plug everything in. Your M1, your T1, M1 is your 0 and 5. Your slope is your 35 over 4. Solve for M. And once you solve for M, what's the last thing we need to do here for part B? Plug in, yeah, do your linear approximation, right? Plug in the 2 minutes into your tangent line equation. Oh, remember, this is non-calculator, so if you're looking at this going, wait, how am I going to simplify that? You don't have to, okay? So calculator, non-calculator section, as soon as you get something that is equivalent to the answer, leave it alone. Don't try to spend time, because if you mess up from here to here, you're going to lose points. So leave your answer unsimplified, especially non-calculator section. So just keep that in mind, right? That you don't have to clean anything up. As long as you have something that is equivalent to the final, to the reduced answer, just leave it alone. Otherwise, you're wasting time doing something that you don't have to do, and then you're inviting the chance of making a mistake.
Yeah, so you have the right answer and you try to simplify it,
you could get a point. Let's say you got like 23.5. You're going to lose a point here because you didn't add, you didn't do your calculations correctly. So don't simplify. Part C. Write an expression for d2m over dt2. What is that asking for? Second derivative. Okay, so here's my dm dt. To find the second derivative, I'm going to distribute that 1/4 through to get myself ready for my second derivative. So I get 1/4 times 40 minus 1/4 m. Now, what's going to happen if I find the second derivative? The left side will become d2m over dt2. What's going to happen with that 1 over 40 times 40? 0. Okay, what's the derivative of 1/4 m? dm dt. Remember, this is with relation to time here, so that m's derivative will turn into a dm dt. So the second derivative will still involve dm dt, but it's 1/4 of dm dt, or negative 1/4 dm dt. So now what can I replace dm dt with? Yeah, back with the original dm dt. Okay, and then from there I can plug in the value that I have from part A, and I just want to look at what that gives me, right? I just care whether it's negative or positive. In this case, this is going to give me a negative number, and negative number means concave down. If it's a concave down, that means my approximation is what? Over approximation, right? If you imagine a concave down graph, any line that skims the surface of that curve is going to sit above the curve. So again, kind of has that related rates feel to it. Remember, time is independent variable, so m just doesn't become 1, it becomes dm dt. Okay. Part D. I put part D on a separate page because it just takes more room. So let's see if we can do part D together here. Okay, I'm going to move on. You guys have the key, so check the key if I'm going too fast for you. Okay, part D, use separation of variables to find the expression for M of t. So solving differential equations, right? So we're going to start off by cross multiplying. What do we want on the left side eventually? Everything in terms of M, and on the right side, everything in terms of t. Yeah. So M is the dependent, T is our quote unquote X. And then don't lose the set of parentheses. The parentheses are there to help you. So don't distribute that 1/4 through. We want to make sure that we separate our variables correctly. So I'm going to start off putting that 4 underneath my 40 minus M so I can get my fractions lined up. Cross multiply. So we should be able to recognize, okay, dm and dt are nicely placed. There's no need to change them. They are where they're supposed to be. But do we have full separation of variables? Okay, so we need to do what? Divide the 40 minus m. Where's that 40 minus m going to end up? Denominator left side. And what else can we move? We don't have to move, but I would suggest that we do move it. Put that 4 where? Denominator. So I can put that as 1/4, right? So if I push that 1/40 minus m out, I have it, and I'm going to push that 1/4 out and just put that, if it's integral of 1 dt, I like to have that 1 sitting there. Okay, the right side, I think it's easy if we can set up this way. What's the integral of 1 dt? It's t, yeah, and the 1/4 will stay, right? And then this, we got to go through a little bit of what? U substitution. U value being 40 minus m, yeah. And there's going to be a leftover what? From our derivative. -1. Yeah, so I keep track of that -1 there. So it ends up being 1/u du with a -1 in front. 1/u is natural log of u, absolute value of u. Replace the u back in terms of 40 minus m. So here's my equation. The right side is 1/4 t plus c. Now, once you're here, if you get up to this point, you should feel pretty good because you've earned the majority of the points. Maybe there's only 1 point remaining. And it's a lot of work for that 1 point. So just keep that in mind. That if you get to this point and you want to solve for C, yes, you're getting to solve for C. If you want to solve for M, but don't get so carried away with this problem that you're spending too much time on this, right? Even though you're like, okay, I know I can do this, I know I can do this. Yeah, if this is 1 point, right? Manage your time accordingly. Sometimes it may not be worth your time to earn that point if there's other problems waiting for you, right? So I would say, give it a try on the exam, but if it's a messy solving for C or solving for M, after you spend a little bit of time, go to the next problem. Make sure you do everything else before you come back to this one. It's not worth spending 10 minutes just to earn 1 point. Okay, so good. We got through half of our 2023 exam problems. Starting on Wednesday, I'm going to have morning and afternoon sessions going through the problems that I did not get to go through in class. And then for homework, you guys will be finishing up the rest of the 2023 problems, 4 through 6, as well as finishing up number 3 that I'll check on Wednesday. But every day after tomorrow, I'm going to send out a daily reminder so you know exactly what I'm checking the following day. All right, come get your phones. Test tomorrow, help session tomorrow morning. Thank you.